in the process of trying to start the broadcast. It says it's on air. I don't see any viewers yet, which means it's still sorting itself through the system. We love this free technology, but there are mysterious aspects to it. So while it's doing that, I'm going to pop up the chat, which I was telling you I was going to do. And then we'll be all set.
Okay.
Yeah. And you're out in California at NASA Ames?
Yeah, I'm based at NASA Ames, yep.
That's one of the niftier architecture NASA sites.
Yes, it's very vintage, very NACA.
Yes, that's true. I'd forgotten that.
Yep.
Sorry, I'm still looking for the chat. It decided to hide on me. We now have a viewer. Yay. Hopefully people are watching. This is what we always hope. It is totally hidden. Let's go to that link. I found the chat. Okay, so if anyone has any questions, go ahead and ask them. And I'm now going to do the official intro to the show, and we'll eventually chop off this beginning. Hello, everyone, and welcome to another episode of the Center for Lunar Science and Exploration Hangouts. We are here this week with Jennifer Heldmann to talk about the SSERVI FINESSE node. SSERVI is a NASA Virtual Institute that studies minor objects throughout our solar system. And by minor objects, I mean asteroids, our own moon, the moons of Mars, these small rocky worlds that come under a variety of different names, all of which we eventually want to land robots, humans, and everything else on, so we can study as much science as possible. This YouTube series that you've landed on, each month we bring on a different science team to talk about how they're working to explore these neat little rocky corners of our solar system. So Jennifer, can you tell us a little bit about what FINESSE is?
Sure, and thanks for that great introduction. So yeah, we're excited. We're one of the teams of this virtual institute. FINESSE stands for Field Investigations to Enable Solar System Science and Exploration. And so essentially what we're interested in is both the science of these rocky worlds. So like you said, focusing on the moon, asteroids, the moons of Mars. What can we learn about them? And for that science, we focus on volcanics and impact cratering, because those are the two most dominant geologic processes that are shaping those worlds. So we study those, and we also are interested in the exploration part. You know, when we go to the moon, go back to the moon, when we go to these asteroids, the moons of Mars, how are we going to explore them? We're going to send robots. We're probably going to send robots first. Well, what kind of robots do we need? What should they measure? What do they need to be able to do? What are their capabilities? What instruments do they need? All of those questions. How are we going to operate them? So we're looking at the robotic aspect and then also the human aspect, because eventually we'd like to send humans to these places. So what are the humans going to do? What are humans good at doing when they get to these destinations? What tools do the humans need? What are their limitations? You know, you're in this big bulky spacesuit. What can you do? What can't you do? And so to get at all of these questions, we study places on Earth that are like the moon, that are like asteroids, or that have attributes that are similar. And so we call these Earth analogs because they're analogous in some respect to these different places. So for the FINESSE work, we have two different field sites on Earth because we can go to Earth. We're all on Earth and we can study Earth relatively low cost, relatively low risk compared to going to the moon or asteroids or Phobos or Deimos. So we go to, for the volcanics research, Craters of the Moon National Monument and Preserve, which is in Idaho. And if you've never been, it's an amazing place. It's incredible. It's got virtually every kind of volcanic feature that you could ever dream of. It's a geologist's dream paradise. So we go to Craters of the Moon in Idaho, and it's a lovely place to visit. There's a little town nearby in Arco, so there's somewhere to stay. So we go and do our field work there. We've gone every year since 2014. We go every summer. So that's for the volcanics work, to study how volcanism shapes our world. And for the impact studies, we've teamed with our partners in Canada, and we've gone up to the West Clearwater impact structure, which is this up in northern Canada. It hasn't been visited since about the 1970s. It's not very well studied at all. And we now know why, because it's really hard to get to. It involves planes, it involves, it's not trivial. But it's really, really interesting because it hasn't been studied, and it's one of the best preserved impact structures that we have on Earth. So we have a team that was led by Western University up in, or the University of Western Ontario up in Canada, and our FINESSE team also partnered with them, and they brought back lots of rock samples. They took lots of observations out in the field. We took some astronauts with us to learn how to do training, and now some of that science is coming out, and we're learning more about the mechanics of impact cratering. We're doing age dating. There are these two craters up there, West Clearwater and East Clearwater, and there's like, basically you look on a map, there's two circles, like two big holes in the Earth. So one would think that those, probably, you know, some asteroid came in and hit and maybe broke apart, formed these impacts at the same time. Turns out that's not the case because they're different ages. Who knew? It's totally weird. That's one of the surprises. So there's interesting science. Yeah, we're still wrapping our brains around that. There's really interesting science coming out. And then also while we're there, for example, at Clearwater, we did some testing for like, okay, what do astronauts need to know when they go, you know, you're on the moon, you're going to study an impact crater. What do we need to train the astronauts to look for? What do they need to know beforehand so that they can collect those observations, collect those samples in the field that the scientists back on Earth need in order to make sense of the geologic story? So that was a really interesting study. There's a paper out on that too about astronaut training, what needs to be done, and then the lab work that happens after the fact as well, bringing those samples back. So it's a really interesting mix of doing science and doing exploration work and doing it. Yes, there it is. There's Clearwater. So we went to the place on the left. It's got these, there's a lake. It's filled in. It's a lake now. It's filled in with water, but it's a depression. And there are rock outcrops all around the edges of the lake. And then also there's that central ring that's in the middle. So we've got samples from there. And there's, if you look real close, in the middle of that circle on the left, there's some little rocks sticking up in the middle, part of the central peak structure that we have samples from there too. So there's some great papers coming out. You can look on Google Scholar and find some of those coming out. So it's a really fun project. We have a really great team of people that get to go out into the field, you know, go to these really interesting places on Earth, learn about the geology, learn about the exploration, and then apply that to help us learn about the moon, help us learn about asteroids. And then there's another component as well, because it's really important because the people that are going to go to the moon, that are going to go to the asteroids, are probably younger than me, probably even younger than you. So we need to train the next generation of scientists and explorers. So we have a program associated with FINESSE called Spaceward Bound. And I love it because what we do is we bring students and teachers out into the field with us. And we bring them into the field and we have them do work side by side with the NASA team. They are right in the mix. They are doing the science, they are collecting the samples, they are running the instruments, and they're taking these experiences back with them, back into their classrooms, into their communities, and doing all sorts of things, infusing this information in their curricula, giving talks, going to science centers, having projects with students, just to bring the excitement. Yes, thank you, Spaceward Bound. Bring that excitement back out into the communities. So that's been really great, and it's been one of the most rewarding parts of this whole project because we can actually make a difference and reach so many different people. So that, in a nutshell, is what FINESSE is all about.
It's a whole lot of amazing stuff, and the enthusiasm that you bring to it shows that you're truly passionate about all the things that you're doing. No, it's kind of awesome to see how cratering is something that has focused so many aspects of your career, including figuring out how to create your own crater on the moon. And
Yes.
and I'd love if you could tell the story of how you went from early career researcher to crashing things into the moon to now leading your own program, because this is really an amazing story.
Sure. Yeah, no, it's been really great. So I'm based out at NASA Ames in California, and that's where I went and I did after my graduate work, and I went to Ames and I did a postdoc and I kind of stayed there. And then as NASA's exploration program was underway, you know, for sending humans back to the moon, to stay this time as a sustainable way of exploring, we're going to need to be able to use resources that are on the moon in order to stay there longer. And one of the main resources that we will probably use is water. H2O, break it apart, hydrogen and oxygen, super important for many, many things. Rocket fuel, not only fueling the base, having operations. So we need to find the water. So NASA came out with a call and they said, look, okay, we have some evidence that we think there might be water ice near the poles of the moon and down in the bottom of these deep craters, because the bottom of these craters, they're at the poles of the moon. Sunlight, basically the rays come, skim across the moon, the bottom and top of the moon, and don't actually reach the bottom of these craters. So there are places on the moon that literally have not seen sunlight for billions of years, which means they're super cold, i.e. colder than Pluto, really cold. So if there's any ice or water that got delivered to the moon from comet impacts, from asteroid impacts, which we're pretty sure has happened, and any of those molecules bounced into those permanently shadowed craters, basically there's no way they're getting out. They don't have enough energy, they're gonna be stuck there. So NASA said, okay, we're going to launch this mission called the Lunar Reconnaissance Orbiter, LRO. It's an orbiter. It's got all sorts of great instruments on it. And you know what? We have enough mass to launch something else too. Something small, something, not too fancy, something you can develop it in 2 years because either the rocket's going to go with it or without it. So work it out. And we want, the goal of this secondary mission, we call it, is to touch the ice. Go there and touch the ice and see if there's ice at the pole of the moon. Give us a yes or no answer because we need to know if we should follow up on this or not. So, it was really fun. It's one of those really fun science experiences where you just get to, think out of the box. Okay, how are we going to do this? It's got to be low cost. It's got to be quick. We got to get into a permanently shadowed region on the moon where we've never been, where it's dark, it's cold, there's no communication with the Earth. What are we going to do? So we came up with this idea. We said, okay, well, we will take the upper stage of that launch vehicle that's launching LRO, and we'll attach a little spacecraft to it. We call it the shepherding spacecraft. And we will just drag that to the moon. There it is. So there's the upper stage of that Atlas launch vehicle. And we'll take it to the moon and we'll crash it into the moon. We're not using it anymore. It's a big empty tin can at this point. Crash it into the moon. And when that happens, a whole plume of debris and dust and junk, ice, if it's there, is going to be lofted above the lunar surface, up above the crater rim into the sunlight where we can finally see it. And then we're going to fly our little shepherding spacecraft through. We'll put some cameras on it, some spectrometers, nothing fancy, but just to see if there's water in that plume. Is there water? And here's a picture of where we impacted. This was, you can see that in that box, that little fuzzy patch, that's actually the impact plume in Cabeus crater near the south pole of the moon. And so we measured that plume, not only from the shepherding spacecraft that we sent to the moon, but also we had a very strong program of ground-based observations, Hubble observations, other spacecraft observations. And to make a long story short, lo and behold, in Cabeus crater, there's lots of water. It's about 5% by weight of water. And sort of the goalpost, what NASA said going in was okay, if there's 1% to 2% of water, might be worth looking into. And then it turns out there's 5%. That's huge. We're wow, that is so interesting. So it was a really great opportunity for someone early in their career like me to be involved in a mission, literally from, okay, let's come up with the idea. Let's write a proposal to NASA and tell them what a great idea it is and why. And then have NASA agree and say, yes, we should do this mission. And they picked it. And then spend 2 years developing it, testing the instruments, making sure they work, integrating them on the spacecraft, going to the launch and having it launch. And then I had got to work in the Science Operations Center, and it's a small mission, so there were only 3 of us in there, during the impact, to see that data coming back in real time. And I'll never forget, we had the science team afterwards, and the first time we were looking at those spectra that were coming back, and there were just lines all over the place, which means, wow, there is a lot of stuff in these permanently shadowed craters. There's water and there's other stuff too. And so it's kind of like the junkyard of the solar system. It's all that stuff that hit the moon early in its history from comets and asteroids, it all got trapped in these not all, but a lot of it got trapped in these permanently shadowed craters. And so there's this record, which is great.
And this was just back in 2009. So this is fairly recently that it happened. And it's actually really helped completely change how we view a lot of these icy objects, because to go back on one of the things you said, in case people missed it, is you said there is water from asteroid impacts. When I was in college taking planetary, which you take like once when you're an astrophysics major, everyone was like, and asteroids are dry and comets are wet, and this is the difference. But it's now looking like it's asteroid impacts that may have delivered the oceans to Earth, the water to the permanently frozen regions on the moon, and some of the crater holes on Mercury, and so many other permanently shadowed regions. And so on one hand, compositionally, we've completely changed how we view things. And then the other thing that happened was many of us stayed up late at night or got up in the middle of the night to watch the impact, and there was nothing to watch.
Yes.
What was like, could you explain this and say what it was like to live through that moment?
Yes. Well, for us, it was very exciting because we were in the Science Operations Center and we knew when it impacted. We knew when we lost signal. We knew when that spacecraft hit. We knew it. We also knew what to expect. And I think, well, maybe it was a lesson in public relations because, all the fancy graphics and, the videos of, oh, here's what's going to look like. And there's this big plume that comes up and it's big dramatic. And that's true. That's what it would have looked like if you were on the surface of the moon at the bottom of Cabeus, right? So I think part of it was a perspective, thing, because sure, if you were close enough and you were sitting there in a lawn chair on the moon and you like watch this big rocket come in and do this big giant debris plume, like, yes, it would be very dramatic. But we are looking at it from way, way, way far back. So we knew our fields of view. We knew what we'd be looking at that time in excruciating detail. So we knew we were going to see a little cloud, which actually was quite large. It would cover like the bulk of, San Francisco, for example. So it was a big debris cloud. But yes, understood. A lot of people waited up really late because it happened, in the wee hours of the morning for most people in the US.
And so many of the news broadcasts had said, and if you have an amateur telescope, you will be able to and no, you couldn't see anything.
No. Yeah, no. And we knew that. We knew that going in because we knew the magnitude wasn't going to be, where you would need it for an amateur telescope. And we did have a very strong ground-based observing campaign. And so we did encourage people, get out, look at the moon, have an event, this is a good opportunity to learn about the moon, that sort of thing. And we had a series of professional telescopes that were looking and have published papers and saw the plume and have found good things and have gotten science results, which is great.
And we actually have some questions from the audience about the plume. We have, I'm going to ask Tom's first because it's shorter. So Tom Van Scooter asks, would that ice sublimate over time?
Yes, very good question. It does sublimate, and it also photodissociates. Once you get up into the sunlight, it starts breaking apart. So we actually just published a paper on this last year. You can go look it up. It's in Icarus, Heldmann et al. 2016. And we looked at exactly that because the signature in the plume changes over time. So it was only about 4 minutes of data we had from the shepherding spacecraft. But even over that 4 minutes, exactly, once you get that ice up above the crater into the sunlight, it sublimates, it breaks apart, it starts changing. The size of the ice crystals we're finding gets smaller because they're shrinking. And so that's telling us something about how it's co-mixed with the dirt, because you can figure out the rate at which those ice crystals are sublimating and breaking apart. And it's depending on, how much dirt is mixed in with that ice and how much energy actually gets absorbed. So it's really interesting. And there's also things happening on the surface too of where the impact happened. So we're also looking at some of the thermal data. That's what we want to do next and say, okay, we heated up the surface and there was ice obviously in the ground there. So you've got this warm mass of ice now that's also probably still releasing. So there's another source of the water molecules coming up. So it's very interesting. It's a good question.
There's so much long-term science that's going to come out of this.
Exactly.
So Kyle Carmichael asks, surface age is based on crater numbers, which is based on an assumption of rate. How sure are we of the rate when we start figuring out the ages of the surfaces?
Yeah, so for the moon, we're very lucky in that we have return samples from Apollo, for example, where we've actually been able to take those rocks into the lab and date them very precisely. So we've kind of been able to, quote unquote, ground truth the cratering rate. So we have a pretty good idea of the ages on the moon. If you go to somewhere like Mars, It's a little less certain. We still have a pretty good idea because we have a pretty good idea of how impact cratering worked in the early portion of the solar system when a lot of those craters were forming. But we don't have, the ground truth from multiple locations to really nail that down. But for the moon, we're pretty confident. We know what's going on there. And it also fits in with the general story of the moon, how it formed, how it's evolved since then, and how it's been stable, because it's a big moon around our Earth, relatively speaking. So.
Yes, and any of you who would like to help us count craters on the moon, you can do this with cosmoquest.org. This project is a collaboration of CosmoQuest and the Lunar and Planetary Institute. And for those who are tuning in late, this is the Center for Lunar Science and Exploration monthly hangout. And with us this month is Jennifer Heldmann from the FINESSE SSERVI node, and she's out at NASA Ames. So your career started with throwing large chunks of metal at the moon, which is awesome. And now you're looking to instead throw metal at the moon, actually very carefully engineer potential lunar, prospectors. Can you tell us about today's work that you're doing?
Sure. So yes, we'd like to land a little more gently on the next mission. So since LCROSS gave such interesting results, and as you were saying before, really changed the paradigm of what we know about the moon, because I also learned in school, the moon is dry, no water here, nothing to see here, and now that is completely changed. So we've answered the fundamental question, is there water near the poles of the moon? Yes. Okay, great. But now we have to go the next step, go and understand this a little better, because ultimately what we'd like to do is try and use that water as a resource. So we need to understand its distribution, on scales smaller than one giant impact. So what we would like to do next in the next mission, sort of in the queue, is called Resource Prospector. And this would be a rover mission, a lunar polar rover. They would go to the North Pole or the South Pole of the moon and have instruments on it that can detect ice as we're driving across the moon. Because it turns out, LCROSS impacted in Cabeus crater, permanent shadow, no light, very cold, very bad for a human base. Not where the people are going to go, where it's 40 Kelvin and no sunlight. Not so good. But it turns out what we've learned is that just outside of the permanent shadow, in a variety of places at the North and South Pole of the moon, where you get, 5, 7, 10 plus days of sunlight per year, it's still pretty cold. It's not a lot of sunlight and it's at a low angle. So you really only have to go down in the lunar subsurface a few centimeters, maybe tens of centimeters. And then you're at the same temperatures that you are in the permanent shadow. It's like, aha. So maybe we just have to go through this much lunar dirt and get the ice there in sunlight, in communications with Earth. You can use solar power. It makes life a whole lot better. So the idea is we take Resource Prospector, take this rover, and we drive over those areas in sunlight where you have ice really close to the surface, and you map that out. Because we fundamentally don't understand the distribution on human scales, so to speak. So we've got a payload, there's prospecting instrumentation, a neutron spectrometer that can look or can sense sort of in the upper meter or so, a near-infrared spectrometer that can sense on the surface, a drill so you can get some samples and bring that up. And now you can start to actually get an idea of where is this ice, where is it accessible, how did it get there, all these questions to inform your architecture going forward for human exploration.
Now rovers come in many sizes, shapes, and varieties. There's Moon Express is looking to have their big old wheel, and then of course many of us are familiar with the Mars Exploration Rovers, Spirit and Opportunity, the Mars Science Laboratory, Curiosity. Are you talking bread box or Volkswagen Beetle-sized rover, something in between?
Something in between. Not like giant, don't need anything big. Maybe something a little bigger than a bread box, so you have wheels that are big enough to go over maybe some craters and small rocks. But we take that into account. You don't go to super rocky areas. You don't go over a cliff, that sort of thing. But you don't need anything fancy because you're not doing super fancy things. Basically most of our prospecting and sensing is happening when we're driving, because that's how these instruments work. Cover the terrain and map out these features. And so we're developing the operations because lucky for us, our moon is so close, we can basically operate this rover in real time. which is a very new way of doing things. You know, we can't do that with the Mars rovers. You know, as great as those operations are, it's a very different situation because of the light time delay between Earth and Mars. Whereas the moon, you know, with LCROSS, by the time you get through the Deep Space Network and back and forth, it's about 6 seconds or so. So that, you know, that's short enough time that you can say, that's something interesting, stop. And that's exactly the concept of operations for this. The scientists are in the science back room, looking at the data in real time as it comes back, and watching, and basically you yell stop if you want it to stop.
And what's amazing is the bulk of that time is actually from the Deep Space Network to the scientists, because the moon is like a light second away.
Yes, it's like the electronics. Yeah, exactly.
So, and for comparison, for those who haven't thought about shooting lasers off the moon, because why not? The moon is about a second away, and Mars is 20 to 40 minutes away, depending on which side of the sun it is from us. And so that's a significant difference. Yelling stop at someone 20 minutes away, they're not going to stop in time.
Exactly.
So this sounds like you're looking at some really amazing upcoming opportunities. You have chances for schools to get involved. You are doing engineering and science and bringing all of these core concepts together to figure out, well, is the moon a moon is a harsh mistress, or is it a moon of, well, this is our next arc from Seven Eves? That's pretty awesome to think about. So if someone wants to learn more about what you're doing, where can they go to find out more?
A good resource is going to the SSERVI website, which is the Solar System Exploration Research Virtual Institute. And that's sort of the umbrella parent organization for many of these teams that you're hearing about in this series. So there's information there. And then we also have our own team website, which is the FINESSE team. So you can just Google that, since we're on a Google Hangout, and look for that. And also there's a resource prospector website NASA has as well, if you want to hear more about this upcoming mission and what that's all about and the work that's been going on to get ready for that.
And you have a Twitter handle for your program for people who want to keep track of things on Twitter, and that's finesse_NASA.
Yes, correct.
And if people only remember one thing from today, other than your Twitter handle, what one takeaway would you want people to have?
That exploration is for everyone.
That is entirely true. And anyone can get involved and do amazing things.
Yes.
So this has been a remarkably fast moving hangout, and I hope that we get to have you on again, because I know there is so much more that we could talk about, but we're out of time for today. Already. So we're just gonna have to have you back.
Yes, that was great.
So everyone out there, thank you for joining us, and go check out the SSERVI website. It is SSERVI, SSERVI.nasa.gov. And join us next month on May 17th, when we're going to have Dr. Dave Blewett of Johns Hopkins University, who works with the Vortices SSERVI note, because I think SSERVI notes are required to have awesome acronyms. And he's going to be on and talking about the search for meteorites in Antarctica. So please join us next month. And until then, have a wonderful morning, afternoon, evening, no matter where you might be in the world. Thanks a lot, Jennifer. This has been a great hangout.
Thanks very much.